Hello and welcome to the Year 9 exam paper. The purpose of this video is to review the exam paper you've just taken. It's difficult to give proper feedback, obviously remotely, so the idea is that you'll have your paper and the exam paper in front of you, and you can scan through it and look to see where you've gone wrong and what you can do to improve it. Now, if you've got any more questions, if you think your mark's been given unfairly or something like that, please do email myself or your subject teacher. But bear in mind that there are slight variations in marking, so it might not be your benefit and marks may go up or may go down. So we'll start off with question 1. And this is for the second paper. I don't have access to the multiple choice paper, so I'm only going to review the second paper on this. So question 1, a student uses some everyday items to investigate static electricity. We shall have a flexible plastic strip being rubbed with a cloth. And we've got to complete the sentence. Rubbing the plastic strip with the cloth causes the strip to become negatively charged because electrons. With static electricity and current electricity, it is always electrons that move. Protons can't move because they make up the nucleus of the atom, they're fixed in place. So it is always the electrons. And this leaves the cloth with a something charge. So what we have is some charges here, a random amount, and then some of the electrons have been transferred over to this way, so we get an excess of electrons over here, and that means that we are left, oops, that's a little bit big, do that again, that means that we are left with a surplus of positive charge on this side. So this side becomes positive charge and that side becomes negative charge. So the cloth is left with a positive charge. Even though it's only the electrons that move, we can still have a positive charge if we take electrons away from something. Okay, question C. So we have a wooden rod and a plastic strip, and the ends are being moved away, and crucially they look like they've been moved an equal distance away from each other, balancing the force of gravity. So the two conclusions we can make from this is it must be a repulsive force because they're pushing away, and the second conclusion is that it must be an equal force because they're both being moved by exactly the same amount. And that's it for question 1. On to question 2. So we have a forces acting on a model air-powered rocket just after it's been launched vertically upwards. How does the velocity of the rocket change as the rocket moves upwards? I can see the misconceptions with this question, in that many people said that the rocket accelerates, which some rockets do. But this is an air-powered rocket, so it has basically one kick, an initial force, and then after that it's following Newton's laws. We're already going to have its weight and air resistance acting against it. It doesn't continue to add thrust just after it's been launched. It's almost like throwing a ball in the air. So the velocity as it moves upwards is going to actually decrease. And the reason for this is that we have basically its weight, mg, acting down there, and we have its air resistance, let's call that AR. So the resultant force, and there is no thrust now, not with an air-powered rocket. It gives it all, gives it all in one kick. The resultant force acts in the opposite direction. So that's obviously 1 mark for getting decrease and 1 mark for saying resultant force acts in the opposite direction. Part 2. The velocity of the rocket is not the same as the speed. What is the difference between velocity of an object and the speed of an object? Well, velocity is a vector, And for the mark, that's all you need to write. But it's worth knowing what a vector is, which is a quantity which has magnitude and direction. So that's different to speed. It has magnitude, its size, and we have to quote technically an angle or a direction with it. So you might say 10 meters per second heading straight up, or 15 meters per second due north, or something like that. Part B, the speed of the rocket just after being launched is 12 meters per second. So let's always write these things down as soon as we get them. So we know speed, not velocity, but speed is 12 meters per second, and the mass is 0.05 kilograms. Okay. Calculate the kinetic energy of the rocket just after being launched. So the first thing we do with any question like this is to always check we've got the right unit. Meters per second is a standard unit, 0.05 kilograms, that's a standard unit as well, so we don't need to convert anything before we start. Next thing we need to do is recall the kinetic energy equation, which is half mass times velocity squared. I know it says speed, but we can use speed and velocity as the same thing in this case. And you're going to have to learn this equation, I'm afraid. There's no getting away from it. It's a very important one. It'll be on the required equation sheet. You must start learning these equations. So now it's just a case of plugging in the numbers. I think the only mistake people may make is it's half times 0.05 times 12 squared. Don't do the half mv and then square the whole lot. That will give a different answer. That's not what we want. And that gives us 3.6 joules. Capital J for joules. Part 2. As the rocket moves upwards, it gains gravitational potential energy. State the maximum gravitational potential energy gained by the rocket. Ignore the effect of air resistance. Well, we could try and use GPE equals mgh, which is the equation for gravitational potential energy, but the problem with that is that we don't actually know h. We know the mass, we know g, we don't know h, so that's not really going to be of much use to us. However, what I can say is to try and do an energy transfer diagram. So I do know that Ke, in this case, the kinetic energy of the rocket, gets converted into gravitational potential energy. And we're going to assume that all of this 3.6 joules is converted into gravitational potential energy. So the answer is going to be the same as your answer to part 1, which is 3.6 joules. Now, if you've got a different answer over here, and you write the same answer there, you should probably get a mark, error carried forward. So we know that's a perfect energy transfer. All the kinetic energy has been converted into gravitational potential. In reality, that's never really the case. You can never have 100% energy transfer. Some of it will be lost to air resistance, so this will give the maximum theoretical. It will never quite reach that. Okay, 3.6. Now, the next bit. Make this a bit bigger. The next one, we're going to try and calculate the height that the rocket goes to. Now, I know from the other part that the gravitational potential energy is equal to 3.6 joules. Now, with that bit of information and the rocket's mass, I am able to calculate the height. Another required equation, GPE is mass times gravity times height. Again, we need to learn that equation. It's a really important one. No getting away from it. And what we need to do now is rearrange this equation for h, because it wants to find out its maximum height. So we'll do this just in one stage. All I need to do is eliminate the m and the g. So we're going to divide both sides by mg, like that, which is going to cancel everything out. And GPE over mg equals h. Or, let's put some numbers in here, 3.6 divided by, what was the mass, 0.05 times 9.8. I think you'd be okay to use 10 and to two significant figures, that will give you about 7.2 metres. So that's how you would calculate the height. And again, like the previous one, it wouldn't really get to that height because it would lose some energy to air resistance. So it would be slightly less than that. But if it's in a vacuum, if it was a perfect energy transfer, that would be the maximum height it could get to. Right, moving on to question 3. So, an electricity one. So the current in a circuit depends on the potential difference provided by the cells and the total resistance of the circuit. Using correct circuit symbols, draw a diagram to show how you would connect 1.5 volt cells to give a PD of 6 volts. Well, voltage in series simply adds together or share. So all I really need to do is I've got 6 volts, I've got 1.5 volt cells. It should be quite obvious that 4 of these in series would give 6 volts. Remember, a cell is a small line and a large line, so we connect them up like that, and that would be our answer. We don't need to connect any other circuits. I think we'd ignore anything else you've drawn on that, but make sure that these things are all in the same direction. It is not something like that. In this case, the two cells will be pointing against each other and the voltages would cancel each other out. Right, I'll try and give myself a bit of space for the next one. So this next question, I think quite a few people struggled with, but it really isn't too difficult. We've got an 18 volt cell, so that's 18 volt battery, which is a number of cells connected together. We've got 2 amps flowing there, and we've got 2 resistors. We know one is a 3 ohm resistor, and we don't know what the other one is, but we can work this out. So first question, question 1, calculate the PD across X. So PD is voltage, effectively. So when they say PD, they mean potential difference, they mean the voltage across a certain component. We're going to use Ohm's law for this, which you can use at any point if it's an ohmic conductor. Voltage is current times resistance. So because it's a series circuit, we should have identified that at the start. We know that the current is the same. This 2 amps over here will be 2 amps at any point in the circuit, through the 3 ohm, through this mystery resistor, even through the cell. It will always be 2 amps. So I know I've got 2 amps flowing through resistor, and I know it's 3 ohms, so the answer should be quite obvious. It is 6 volts. Excuse me. Now, what I would always do with these types of questions is write that on somewhere. It can help you. As soon as you work something out, write it in the circuit. Part 2, calculate the potential difference across Y, across the other one. So we've got another voltage across here. Now I don't know what the resistance is, so you might think, how on earth can I solve this? But I do know that of this 18 volts at the top, because these are in series, voltage is shared in series, not in parallel. It's the same in parallel, but it's shared in series. So really, I've started off with 18, I'm going to lose 6, I'm going to have 12. It's just 18 minus 6, which gives you 12 volts. Nice and simple. Part 3, and again I will write this on up here. Now we want to work out the resistance of this mystery component Y. I'm going to use Ohm's law again. V equals IR. This time I know the voltage, the current is the same. It's a series circuit, so the current will not change. I need to manipulate this, so I need to swap it around. So that will be V over I. You can use a formula triangle if you want. I'm not a massive fan of them, but they do work. The voltage is going to be this 12 volts over here, not anything else. So it's 12 divided by the current, which is going to be 2, which gives us 6. That is for component Y, so that will be 6 ohms. But the question actually asks us for the total resistance of X and Y. So we need to add this one and that one, 6 plus 3, to give our final answer. Resistances in series also, like voltages, add together. Very, very easy. Right, moving on to the space question. Get rid of all this. I won't write out the full question, it will take too long. 8 planets in the orbit around the Sun. There used to be 9 in my day, but hey ho. What are the types of objects orbits the Sun? Well, the answer is going to be a dwarf planet. Obviously, it's not going to be a star because the Sun is a star. It's not going to be a galaxy because the galaxy is a collection of stars. I can understand why some people have written moon, but the moon orbits the Earth. It doesn't. I know it goes around the Sun, but it goes around the Earth primarily. So the answer is going to be dwarf planet. Got an R in it. Dwarf planet. Another complete the sentences, choosing answers from the box. So again, I'll just read this out. The Sun was formed, well, we've got black hole, gravity, friction, nebula, protostar, and upthrust. It might be worth us, before we're doing this, just reminding ourselves of the basic life cycle of a star. So we start off with a nebula, which is a cloud of dust and gas, mainly. That will go to a protostar. Then it goes to a main sequence. And again, this is something that you really need to memorise, certainly for your GCSE exams. Then the main sequence will go into 2 different ways. It can go to a red giant or a red supergiant. There's actually 3. There's red hypergiants as well, but we won't look at them. And then that will cool to form a white dwarf. Whereas if it's big over here, the red supergiant will go into a supernova where it will explode violently, and then either a black hole or a neutron star. You may ask what determines the path it takes at kind of this point here, and that's its mass. If it's a large mass, it will turn into a red supergiant that will go into supernova. If it's a small or average size mass, it will do a red giant and a white dwarf. And I think it's also important to state this is a very simplified version of what actually goes on. There's different possibilities, and there's different things that will happen after to the black hole and the neutron star and the white dwarf. But this is the basic one. This is the one that you need to memorise for your GCSE. So the Sun was formed, quite obviously now, when a nebula in space was pulled together by gravity. It's gravity which contracts it all, which brings it into a protostar. The gravity compresses it, and then the heat from the friction heating initiates the nuclear fusion, and we go to the main sequence. The Sun has reached the main sequence stage in its life cycle. What stage in the life cycle of the Sun will follow the main sequence stage? So looking at this, it's quite obvious it will go to a, what's it, this is C, this is red giant. Now, you may be given a mark if you say red supergiant or red hypergiant. Technically, that's not true. The Sun isn't big enough to go through that. It will enlarge to a red giant, and then it will cool down into a white dwarf. It won't go supernova. It won't explode. But you may get a mark for it at this stage, but it's not really worth it. I think at GCSE there is an important difference between this term red giant and this term red supergiant, because they are different things, and different things happen to them after they burn through their helium. Next one, we've got some data about the 8 planets that orbit the Sun. What pattern links a distance a planet is from the Sun, and the time taken from the planet to orbit the Sun. Now, look at the mark scheme. This is only 1 mark. There's no point writing an essay for 1 mark. If I can look at the left-hand column, 0.4, 0.71, 1.5, that's the distance, and the time, 0.2, 0.6, 1, 1.9, 12. Clearly, as the distance increases, the time of orbit increases. And that's all you need. You don't need to make it any more complicated than that. If you look at it, you'll see that it's not actually a proportional relationship. It actually follows a t squared r cubed relationship. It's quite a complicated one called Kepler's law, which you wouldn't really be dealt with until A-level physics, in fact year 13 physics. So that's all we need for now. Distance increases, the time of the orbit increases. The planets which are further away will rotate longer. I mean, things like Neptune, you can see that that's 165 Earth years, which is quite spectacular. That means it's not even done like a tenth of an orbit in your entire life, even though you guys have done 14 or 15 of them. Estimate the value of x. Now, looking at the pattern here, we need something between 1.5 and the next one, 9.6. I would not expect you to give an accurate estimation for this. So you can pick any number, I don't know, go for 4.0 or something like that. But essentially any number between 1.5 and 9.6 will be okay for that one. Right, moving on to the next bit. Student looks at the data. The mean surface temperature of the planet decreases the further the planet is from the sun. Explain why this conclusion is not correct. So we've got a few different points here. It's worth 3 marks, so we need 3 points. Really, it should be obvious that some planets don't fit the description. That's only going to score you one mark. Then you need to name a planet. If you can give an example. And if you ever get these questions at GCSE where you're given a table of data and you're asked to do something with that data, always try and pick an example from it. The second mark is nearly always from that. And so you name the planet and then give a reason why that planet doesn't fit the data. There's a couple of answers you could have here. So you could have something like Uranus, its temperature is lower than expected, or Neptune, its temperature is higher than expected, or Mercury, its temperature is lower than expected, etc., etc. There's quite a few different ones you can have, but basically some planets don't fit. Name one of those planets and give a reason specific to that planet as to why it doesn't fit, and that will be your answer. Right, question 5. So we've got a circuit here, a few components in. We've got a variable resistor, we've got a fixed resistor R, an ammeter, and a voltmeter wired in parallel, that's correct. And we're going to describe how a student would use this circuit to take the readings necessary to determine the resistance of resistor R. Okay, so this is a very standard experiment, an Ohm's law practical or an IV characteristics practical. You will do this as a required practical, whether you do dual or triple, makes no difference. This is a really important one. Let's read the question. Describe how a student would use the circuit to take the readings necessary to determine the resistance. Not how you'd calculate it. I mean, you can mention that, but strictly speaking, that's not what we're looking for, just the measurements we take. So, basically, you could have any 6 from the following points. Nearly forgot as well. There is, of course, a switch in there. So, switch on, obviously. Now, I know you may think it's obvious, but there's a mark for that. Use the switch, turn the circuit on. Okay, read the ammeter and the voltmeter. That's another mark. Again, you might think it's obvious, but maybe not. The next thing is we're going to use the variable resistor here to adjust the current. So adjust current and name it using variable resistor. And then we could take some repeat readings perhaps. So you can repeat 3 times for each one, take some more, and then draw a graph. Now typically this is done as current against voltage. In this case you should get a nice straight line if your current is fairly low, and that's largely it. If you wanted to calculate the resistance, then the resistance would be the reciprocal of the gradient, which means 1 over the gradient of the IV. But it doesn't actually say to do that, it just says describe how a student would use the circuit to take the readings necessary. So you're kind of given all that. And as ever with the 6 marker, there's going to be a QWC mark, which is going to be very difficult for me to go through here. That's quality of written communication. Have you used the right terminology? Is your spelling right? People are always asking me, does spelling matter? Yes, it does. Even in a science exam, it's always important. In a question like this, there will be a mark for it. Part 2, explain why the student should open the switch after each reading. That's simply because the resistor will get too hot. If you leave it on, it may overheat. Now, that might not be a problem as in it's going to set fire or be dangerous, but this will increase the resistance. Hot objects tend to have a higher resistance, so the resistance will be getting bigger and bigger as it gets hotter and hotter and hotter, which means it's not going to be very consistent. And you might have to put a fair bit of current through it, so close the switch, take your reading, take it off. If you leave it on, the actual resistance is going to change, and this gradient down here will not be a straight line, it won't really be obeying Ohm's law. So that's really important, and it's also a safety thing as well. We don't want to be having hot components that are going to catch fire. That really wouldn't be very good. Okay, part 3. In an experiment in this circuit, the ammeter reading was 0.75, so A was 0.75 amps, and the calculated value of the resistor was 16, so R equals 16 ohms. What is the voltmeter reading? Well, it's just Ohm's law. V equals IR, so 0.75 times 16 gives you 12 volts. And finally, part 4, the student told his teacher that the resistance of resistor R was 16 ohms. The teacher explained that the resistors used could have only been one of the following values. Which one had he used? We have a 10, a 12, a 15, an 18 and a 22. What it's going to be is a 15 ohms. It's the obvious answer, it's closest. You don't need to be clever with that or anything. It's 15 is the closest one to 16 out of the choices that we've got. And that concludes the exam, I think. Yep, that's the lot. No more questions, so please do use this again, make your corrections, and I hope this has been of help to you. Thank you very much.